we have to, sort of start with what we call as the inverse Laplace transform. Just a minute, guys. What we call as the inverse Laplace transforms. Okay. Now, why? First of all, why do we need it? Okay. Now, as I said in the previous class, that the objective of talking of Laplace transforms was to convert the given differential equation that we wish to solve into an algebraic equation, right? Because once that happens, then it becomes easier to solve algebraic equations compared to differential equations. So once we have a differential equation converted into an algebraic equation, we just have to find the kind of roots, right? But then again, the roots or everything else would be, in terms of the derivatives or something like that. So that means to get things back also, we must know if Laplace transform is doing this, then can we convert back or can we move a step back also, right? So that means that means what? That means given some algebraic expression, can we talk of the corresponding Laplace transform to it? Because what you have done so far is we have learned how to find the Laplace transforms of certain standard functions, like for example, uh, of polynomials, of cos kx, of cos hyperbolic kx, and things like that. So what we have learned is we have learned how to find the Laplace transform of that. The thing is that once we are given something in terms of a Laplace transform, can we get back the original function? That is the objective. Okay, so to do that, we need the converse of inverse Laplace transforms. But before we actually move over to the concept of inverse Laplace transform, there are a few things that we need to be sure of. Okay, the first one being that we have to be sure that a particular function or particular expression that we are talking of has a Laplace transform. Okay, so that means we also have to talk of the existence of Laplace transform. Abhi humne kya kiya tha? So far, we just learned the procedure of finding the Laplace transform. That means nowhere did we impose a condition, nowhere did we check whether for the given expression the Laplace transform would exist or not. We never checked it. We just assumed that it will exist and we just obtained that transform, right? So, but then it may not happen for all kind of expressions. It may not happen for all kinds of functions. So so to be sure that a particular Laplace transform exists, we must have some condition, some rule, so that we are sure of it. Okay, so that is one thing. This is the most important theorem that we are going to talk of here, that a Laplace transform exists, and if it exists, then under what condition does it exist? So we need to first of all verify and ensure that those conditions are satisfied. Okay, but before we move over to that theorem, there are a few concepts that we need to talk of. The very first being what we call as the piecewise continuous functions. Okay. Now, so far you have learned about continuity in an interval AB, right? I mean, I'm not going into that calculus definition of continuity. I know you have been studying it right from class 11, 12, right? So you know when a function is going to be continuous, when a function is going to be discontinuous. Like now, the moment, say what should happen is that when we talk of continuous functions, the functions that should come to your mind are trigonometric functions, polynomials, I mean, not rational, but polynomials, or say exponential functions, right? The moment we talk of discontinuous function, the very first, immediately, you should talk of step function, because we know that it is discontinuous at specific points, right? Now, just look at step function. I'll just go graphically, right? Just look at step functions. Something like this. You have, this is how the graph works. Right? So you have discontinuities at these points. So supposing my interval is, say, 0 to 4. Okay. This is how the graph will work. Right. Now, if I consider my whole study or my whole analysis in the interval 0 to 4, obviously this function is a discontinuous function, right? So obviously, whatever theorems, whatever results exist for continuous functions cannot be applied to this function in the interval 0 to 4. Okay. But supposing I say, okay, let me not consider the whole thing. Let me break it into pieces. This is what piecewise means. Okay. So supposing I just consider 1, and that to an open interval from 1, the function is continuous. Right or wrong? Similarly, from 1 to 2, it is continuous. 2 to 3, 3 to 4. So what have I done? I have, in a way, split my interval into sub-intervals. This is what we are doing. We are splitting our interval into sub-intervals in such a manner that there are only finite number of points. See, this is important. I have only finite number of points at which my function is discontinuous. I cannot say that it is discontinuous at infinitely many points. No. I can pick up points 1, 2, 3, 4. I mean, 4 also inclusive. Okay, fine. So there are only finite number of points at which my function happens to be discontinuous. And I can split my interval. That means what? That means I pick up those finite points of discontinuity, right? And I split my interval so that my function becomes continuous at each of this sub-interval. If this happens, then the function is said to be piecewise continuous function. Is this clear? See, I have not even given you the formal definition so far. It's just that I've just explained the concept to you. Is it okay or not?
Yes, ma'am.
Is it okay?
Yes, ma'am.
So basically, if you just see the definition of piecewise discontinuous functions, piecewise continuous functions, these are the two conditions that need to be satisfied. Okay. So basically, what are we doing? We have an interval AB. Okay. And the interval AB is such that there, say, I can find there are at, say, I have an interval AB with A less than or equal to B. I can find finite number of points, say tk, where k from 1 to m such that tk minus 1 is less than tk, and the interval is such that a, I mean, of course, greater than or equal to 0 is less than or equal to tk is less than or equal to b, right? This is how my interval can be subdivided, and these are finite in number. Okay, so I can have a less than or equal to t1, less than or equal to t2, so on, less than or equal to tm, and less than or equal to b. Okay, so this is how we have partitioned our interval, right? And in each of these subintervals, the function happens to be continuous. So basically, what we are talking of here is that my function, discontinuity kab hota hai? When we are plotting a graph and we have to pick up our pencil, while plotting it. So that means there is a jump. So the only thing that we have now to be careful is that the function has finite number of jumps, and these jumps will be your finite number of discontinuities. Okay. Now, if this happens, then we have, then the function is said to be a piecewise continuous function. Now, since we are talking of a step function here, so let us, like the example 8 in your book, it talks of the Laplace transform for a step function, right? Now, how do we define a step function? Of course, we had defined as 1 or 0. So now notation for step function is like we define the step function as ua of t, which is defined as some function of t minus a, which is going to be 0 for t less than a and 1 for t more than or equal to a. This is how the step function is going to be defined. Okay, this is the definition for a step function that we are going to use now onwards. Is this okay? And the graph is, of course, see your now why I have specified a, because the one that you know is a step function with you can say steps of 1 units each. Okay, na? So 0 to 1, 1 to 2, 2 to 3, and so on and so forth. So this is going to be kind of a step function with steps of a units each. So a can be 1, a can be 2, a can be anything, right? So this is a general definition of a step function. Okay, we defined it as u of t minus a, which is 0 for t less than a and 1 for t more than or equal to a. Is this clear? Huh? Just see it once again, and if there is a problem, otherwise you can look it up in the book also. They have explained it there. Okay. Is it fine? Huh? Okay. Now let us find the Laplace transform for this step function. But see, this is interesting. You know, though you must have, while doing problems, you must have seen a table on page number 456. You know, table number 7.1.2. Is it, do you have it in your hand? Can you see it now?
Yes, ma'am.
Right. So the last entry in that table where ft is u of t minus a. Okay, that has been proved as something, right? We did not derive it, right? So now if you derive it, it's basically nothing but the Laplace transform of ua of t. Okay, which is going to be, if you go by the, I mean, just try it yourself. How do you find the Laplace transforms of any function? So it is going to be the Laplace transform of u of t minus a, which is defined like the one here. And how do you define the Laplace transform? It's 0 to infinity, right? E to the power minus st into ft. And what is your ft? U of t minus a dt. Yahi hai na? Now, u of t minus a is 0 for t less than a. So that means this term will be 0 for which values of t that are less than a. And it is going to be 1 for t more than or equal to a. Okay, so that means this integral is going to be the integral a to infinity e to the power minus st dt, because it is going to be 1. Now, can you not evaluate this integral? What will be the value of this integral? Hmm?
e to the power minus st by minus s.
E to the power minus st upon minus s, but the limits being from a to infinity,
Yes, ma'am.
right? So when you take the limits, what do you get?
E to the power minus as by minus a minus
E
s
to the power a minus as by s.
minus
माइनस
s.
साइन हट जाएगा ना अब.
Yes, ma'am. Lower limit.
हाँ, lower limit. So this is the Laplace transform for a step function. Okay, so if your step is 1 unit, it's going to be e to the power minus s by s. If your step is going to be 2 units, so on and so forth. So this becomes the Laplace transform. And this you can see is your last entry. यही है ना? Now, once we have defined the piecewise continuity, we need to define another concept which is called as the function of exponential order. Okay, this is one more thing that we need to define. What do we mean by a function of exponential order? Okay, now see what happens is that I'll just go by the definition and then try to explain the definition here. We say that a function ft, I'm writing it for you, a function ft is said to be of exponential order alpha. See, now this order also has a parameter attached to it, exponential order alpha, if what happens? If there exists constants, of course, alpha and m, both more than 0, m more than 0, such that what happens? That the modulus of the function is always less than or equal to m e to the power alpha t, where t is more than or equal to 0. Okay. Now, if this happens, then the function is said to be a function of exponential order. Okay. Not just this, to verify, I mean, this is the definition of functions of exponential order. But to verify whether a function is of an exponential order or not, what we can do is we evaluate certain limits. Okay. I mean, the limits being, you don't see, you will be given a function ft and you will be asked to test whether it is of exponential order or not. So what we do is we simply evaluate limit t as approaches infinity, ft upon e to the power alpha t. Okay. If this limit is finite, then the function is said to be, of exponential order alpha. Otherwise, it is not. Okay. We'll come to it we will come to it when we do problems based on exponential order. But this is how we are going to test whether it is of exponential order or not. I mean, there are certain relations. Do you remember it? Do you have any relation between the graphs of cos t and e to the power t? याद है कुछ? किया था ऐसा कुछ? Okay, just in your notebooks right now, you have a graph of cos t. On the same graph, you can plot the graph of e to the power t also. What do you observe? Okay, not just cos t. Just observes the graph of t and e to the power t. What do you observe?
Ma'am, they are not intersecting.
No, they are not intersecting. Fine. Which graph lies where? I mean, Which graph is above and which graph is below?
Ma'am, e to the power t is above.
E to the power t is above the graph of what? T.
T.
For every value of t. So basically what you
Yes,
can
ma'am.
see from here is that mod t is always going to be less than or equal to e to the power t. Can we say that? Just looking at the graph. कह सकते हैं?
Yes, ma'am.
What do we want? This relation. यही चाहिए ना? For what values of t? More than or equal to 0. So if you compare this, that means what? If you compare this with that expression, m e to the power alpha t, what does it mean? M is 1, alpha is 1. That means what? That means t is a exponential function of order alpha. Is it okay? Similarly, cos t and et, right? So just these are certain, see, that's why, because t is an exponential function of order 1, in fact, alpha kya ho gaya tha isme? 1. And t is a continuous function. That's why Laplace transform for t exists. Similarly, Laplace transform for cos t exists. But look at this e to the power ct square. If my ft is this, if my ft is e to the power ct square, and I want to test whether this function is an exponential function of order alpha or not, right? Now, I say it is not. Why? Because just evaluate limit t tending to infinity e to the power ct square upon e to the power alpha t. What does it turn out to be? I can write it as limit t tending to infinity e to the power ct into t minus alpha. Okay. And mind you, your alpha is greater than 0, your t is also more than or equal to 0. What does this limit turn out to be?
Infinity.
फिर से बोलो.
Ma'am, e to the power
Can you say that
infinity is
again? I didn't hear
infinity.
you. It
Ma'am,
is infinite.
infinity.
Infinity. That means what? This limit is not finite. Therefore, this function is not a function of exponential order. Okay. Now, the thing is that why is this concept so important? Okay. This is because if you just look at your theorem number 2, which talks of the existence of Laplace transforms, it says that if, number 1, a function f is piecewise continuous. So this is, this condition is very good. We need not want our function to be continuous in the whole interval. Even if it's piecewise continuous, we are good with it. Okay. The only thing is that we want only finite number of discontinuities. Okay. Number 1, it is piecewise continuous. Sorry, did I write continuity? Okay. A function f is piecewise continuous for t more than or equal to 0. ठीक है? Secondly, is of exponential order. Okay, the order can be anything. The order is alpha basically as t approaches infinity. Okay, if these two conditions are satisfied, then the theorem says that its Laplace transform, which we have defined as what? Laplace transform of ft, we have defined as f of s. We say that this exists. Okay, so basically, what do we want? We want that the function should be piecewise continuous, and the function should be such that it should be less than or equal to m e to the power alpha t. Okay. For t more than or equal to 0 or for some constant, then the Laplace transform exists. So basically this theorem, just guarantees that for every function the Laplace transform may not exist. But it exists if these two conditions are satisfied. Okay. And not just this, as a corollary to this result, we have another result which says that if the function satisfies all the hypotheses, then see, what was your f of s? This was Laplace of ft, right? We had till now imposed conditions only on t, right? The corollary though says that limit s tending to infinity f of s will always be 0. That means what? See, this is another thing. This means that for this function to exist, see, what is this function? The Laplace transform of ft. For capital Fs to exist, my small ft must satisfy two conditions, right? That means if my small ft satisfies these two conditions, then not only does this capital Fs exists, but this capital Fs behaves in this manner. That means what? That means as my s becomes larger and larger, my Fs will be 0. Okay, so it is going to be convergent always if the Laplace transform exists. Not just this, in fact, we have uniqueness of Laplace transforms also. Okay, this is your theorem number 3. Okay, so if you have two functions, ft and gt, that satisfy the hypothesis for the existence of Laplace theorem, so that means what? Both capital Fs and capital Gs exist. Okay. Then the theorem says that if capital Fs is equal to capital Gs for all s greater than some number c, for some c, okay, may not be for all values of s, but maybe for some s greater than c. Say, जैसे functions behave करते हैं, maybe for a finite number of beginning terms, they may differ, but then later on they are all equal. Then the theorem says that the functions, ft and gt must be equal, but where? On the interval 0 to infinity, where both f and g are continuous. Now, this is also an important result. See, just compare this result with the derivatives result. Kya tha? If you have two functions whose derivatives are equal, then the functions differ by a constant. ये हमारे पास standard result है, right? In a similar manner, if I have two functions, small f and small g, such that their Laplace transforms are equal, but obviously may not be equal for all s, but may equal for some s greater than c. So this amounts to saying that they are equal for infinitely many values of s, then they can be equal. See, why this is important? Because for both small f and small g, capital F and capital G exist. उनकी existence के लिए क्या condition है? That my functions have to be piecewise continuous. So if they are continuous everywhere, then their functions are also going to be continuous everywhere, right? But if they are piecewise continuous, then it could be possible that small f has different points of discontinuities and small g has different points of discontinuities, right? So I mean, how to conclude that they are going to be equal, small f and small g? So they are going to be equal only on those points where both of them are continuous. Okay, so that means we have to remove the common points of discontinuities and we have to talk only of those points of continuity, those intervals of continuities which are common for both f and g. Then only in that subintervals, this small f and small g will also be equal. Is this clear? बोलो. Is this clear or not? जल्दी बोलो.
मैम ऑलमोस्ट क्लियर.
ऑलमोस्ट क्लियर. फिर क्या क्लियर नहीं है तो वो पूछ लो.
मैम ये सीधा मतलब यही बोल रहा है कि अगर हमारे पास एफ एस और मतलब कैपिटल एफ एस और कैपिटल जी टी एग्जिस्ट कर रहे हैं तो इट मीन्स हमारे स्मॉल एफ टी और जी टी इक्वल होंगे एंड दे मस्ट बी कंटिन्यूअस ऑन इंटरवल 0 to infinity.
No. This means that if the Laplace transforms are equal for two functions, small f and small g, if their corresponding Laplace transforms are equal, then the functions will be equal only on those points where both of them are continuous. अब बताओ.
मैम इसमें मतलब कुछ ऐसे पॉइंट्स भी हो सकते हैं जहाँ पे ये दोनों मतलब सेम पॉइंट पे डिसकंटिन्यूटी इनकी ना हो, तो हमको सिर्फ वो वाला इंटरवल लेना है जिसमें हमारी सेम डिसकंटिन्यूटी हो दोनों उस इंटरवल पे.
हाँ, मतलब सिर्फ उन्हीं जगह पे इक्वल होंगे, बाकी जगह पे इक्वल हो भी सकते हैं, नहीं भी हो सकते हैं, बट गारंटीड दे वुड बी इक्वल ओनली ऑन दोज पॉइंट्स जहां दोनों के दोनों कंटिन्यूअस है.
ओके मैम.
Okay. Now the thing is that if you just go back to that table, you know, which you have written, I mean, in which we have written the Laplace transforms. Okay. Just for example, you have written that the Laplace transform of t was 1 upon s square for every s more than 0. Okay. So, and this we have seen that if my f of s is the Laplace transform of ft, then my ft will be the inverse Laplace of f of s. Okay. So basically from here, we can say that inverse Laplace of 1 upon s square is going to be t. Okay. So it's like you're working from one function to another. Okay. Now, the thing is that now what I expect you, I mean, I won't do much further today.